All right, everyone, I'm going to be talking about Lab 3, which is on waves. So in the last lab, you learned about simple harmonic oscillation, where we had these sine waves. So that's a type of wave. So just to get into it really quickly, this is what a wave looks like. And there's a few important parameters, which are the wavelength of the wave, which is essentially a measure of like how far stretched apart these peaks are. We have the velocity of the wave, which is how fast the wave is moving. And then we also have the amplitude of the wave, which is from essentially the height of the wave at the peak from like the middle point to the top point here. All right. And then there's also the frequency and the period of the wave. So the frequency is how long it takes for the wave to complete one oscillation. And then the period is just, the period is the time it takes for it to complete one oscillation. And the frequency is the rate at which that happens, or like 1 divided by the period. And so therefore the period is 1 divided by the frequency. All right, so there's two types of waves. So there's transverse waves, which look like this, where the wave is moving up and down, but the oscillation is up and down, but the wave itself is moving to the right. And so we can see that the oscillation is perpendicular to the direction of motion, and so that'd be called transverse. And then longitudinal waves are when the oscillation is in the same direction, which is left and right here, as like the wave is moving. All right, and so like a transverse wave, like A, is like maybe like a string where you move the string up and down. And then for part B, a longitudinal wave would be like a spring where we are compressing it, but the wave is still moving in the same direction. All right, so like the last lab you were looking at longitudinal waves. All right, and so then they give you this wave equation. So this phi naught is just the phase of the wave, and then 2 pi f is like a measure of the essentially it's a measure of how long it'll take for the wave to complete an oscillation, because the frequency is related to the period, and then we're multiplying it times time, right? And then 2 pi over lambda is essentially a measure of how spread apart the wave is, because it's related to the wavelength, and that's what the wavelength tells us. And so the important thing is, like in this lab, we're going to be assuming that phi is 0. So there's no initial phase, and then we're also starting when everything is 0. So this lab is like a lot about, the first part of the lab is about standing waves, where you just have this part of the wave moving up and down, but not to the left or right. Okay, and so that's what a standing wave is. And so we model a standing wave as two different waves that are identical, that are moving in opposite directions. And so that comes from this minus and shifting to a plus. And so when you add these two waves together, you have the standing wave motion, where like a point will move up and down until, or not until anything, but like the wave will just move up and down and not left or right. Okay, and so this is the apparatus you're going to be using. So you have a wire, and then you have a mass here to put tension in the wire, and then you have a function generator, which is just going to generate a sinusoidal signal. It sends that signal to this mechanical drive, and that's going to move this up and down, and then you're going to adjust the frequency on the function generator to try to generate a standing wave. And you'll know it's a standing wave because you won't see the wave moving left or right. All right, and so in this part of the lab, they talk about like how to derive harmonics, and like the frequency you need for each harmonic, and or the wavelength of each harmonic. And I don't want to talk about that because it'll take a while, but I'll certainly answer questions about it during the lab. But essentially, they just use these things called boundary conditions, where we say on the left and right, on the left and right, we know that these 2 points aren't moving, and so we set them equal to 0, and then they just plug in values and they solve for stuff. I'll talk more about that in like the review video after the lab. And so in this lab, like this part of the lab, you're going to be seeing what frequencies generate standing waves, and then you're going to compare, the one you calculated, like you calculate what frequency should generate a standing wave, and you compare that to the frequency you actually observed a standing wave at. All right, you can do that for the different harmonics, meaning different multiples of the frequency. And for the second part of the lab, you're going to do sound waves. So essentially, you're going to connect a speaker to your function generator, and that speaker is going to, output sound waves. And you're going to use a microphone to listen to those sound waves, and you're going to look at different harmonics of specifically 256 hertz. And so what you're going to be actually seeing is data created by something called this fast Fourier transform. So Fourier transforms are like a much more advanced topic than this class would go over. But if you're in like electrical engineering or anything, you'll definitely learn them at some point. All it does is it takes a signal, some periodic signal, and then it outputs essentially like a histogram of the different frequencies in the signal. So if I send in a signal with that's at like 256 hertz, the fast Fourier transform is just going to show me a single box where that's located at 256 hertz. Okay? And so that's all it really does. That's all you need to know. So essentially, if you have a bunch of different frequencies, then you might have, frequencies around it like this. All right? And so you're going to look at 256 hertz, and you're actually going to have, I don't think the lab manual talks about it, but you're going to have a tuning fork, which looks like this. And then when you hit the tuning fork with the mallet we give you, it should output a 256 hertz sound. And then using the function generator, you're going to generate different harmonics of that sound with the speaker, and you're going to look at how they look together. And then this part's 2.11 is pretty important. You should definitely ask me about it in the lab as well, but it says that I'm going to provide you guidance on what's most essential to include. So regarding this, I think the important things to include are, one, all of the signals themselves. So if you're generating these like different harmonics, that's not right there. I might have drawn that incorrectly, but if you're generating these different harmonics, then you're going to want to include all of them in your lab manual. All right, and then the last part of the lab is just a bunch of questions. And then also regarding 2.11, definitely make sure to try to understand, why the different harmonics are shaped how they are relative to the initial function. But regardless, this should be a cool lab, and I look forward to doing it.